Thank you. Yeah, I was just saying, just to review what we did last time quickly. We set up our LM Studio locally for those that can run LM Studio locally. Otherwise, you'll probably need an online LLM. We tried OpenAI library for talking to our LLM, and finally we had tried. Sorry, Catherine, can you set your mic to mute, please?
Catherine?
I'm sorry.
Yeah, no problem. Yeah, there.
Thank you. So yeah, we did try a Llama Index library to talk to our LLM. And basically, what else did we do? Used Llama Index Retriever, right, to basically just ask a question to our LLM. I think that's what we did. So I saw in Discuss that we had a few comments about the exercise, or did anyone find any difficulty or?
That's pretty new to me. I mean, I'll start first with regards to the feedback. Yeah, that's pretty new to me, and it looks promising. Honestly, it's easy to implement or to deploy. I have the local server, and as you have mentioned last time, it's quite interesting that they managed to compress everything in just 5 gig of file, right?
Yeah.
Yeah, that's really interesting. And as you said, it's actually locally running without any external references. That's why I think I mentioned in one of my comments, what if I cut off the internet? Because maybe at some point it's really sneakily,
Did you actually try, turning off your internet?
I haven't. But yeah, I think that's really good. Yeah, from my side. How about anyone else here who would want to give feedback? Oh, LangChain.
Oh, Tony, thank you. Yeah, personally, I've played with LangChain a little bit, but I'm more of a Llama Index guy, so I use that more often than other libraries. I think there were a couple of, I'm not sure, was it Lizzie who mentioned about using the big PC, and the being able to run LM Studio with it. So that's interesting also, because I know it can be a resource hog, this large LM Studio downloading such a large, it's still a quantized language model, but it's still large, right? Like 5 gigabytes worth of it. So. Tony said it's slightly slower than the general, the OpenAI API.
Maybe Lizzie, do you want to say something, Lizzie, or you're on mute?
That's okay.
Yeah, sorry. What had happened with me is I've got a very old MacBook that I'd put a Llama on, and then LM Studio and Visual Studio, and then it just didn't have room for the LLM files as well. So it was a good push to get my PC back up and running.
I would imagine your MacBook to kind of all the fans on and
yeah, it was starting to complain about doing anything. But no, it's all running well. I didn't get the Llama Index thing working, but the rest of it was all working okay with a couple of different models, so that's good.
Right. Okay. I wonder why you can't get the Llama Index working. Did it have any issues about like runtime errors, or anyway? Maybe we can discuss the errors.
Yeah, I'm sure it's me.
Yeah. Okay, that's cool. I think. Yeah, we probably should get going. It's going to be very interesting today. We only have a few minutes. I'll just turn on my timer in front of me so that I am aware of the time. Today will be talking about today's going to be module 3, talking about vector databases and the reason why we need it. I'll start and share my screen so that you'll see the material. It's basically the same, repo you've all been familiar with now in GitHub. And apologies in advance. My voice might break. I'm still under the weather a little bit. But yeah, I've got my menthol candy here with me, lolly, and a jug of water. So sorry. Okay, let me share that. Sorry, no, wrong one. Sorry, I want to share my window actually, not just the screen, because there's things that I want to share. Okay, that one you can see, and then when I shift, all right, it's not working. Let me try again. Okay, that's better. Okay, yep. Okay, so we're in module 3 now. I'm talking about vector databases. Maybe we step back a little bit, or actually fast forward to module 5, just to understand why we need a vector database. So I'm not sure if you've seen this image before, but this is basically what we did in module 2, right? So we have a LLM here and nothing else, nothing else around it. We ask a question, and as we know, a generator is the generator's memory is actually frozen to the time it was last trained. So we know that if you ask a question that it doesn't know about, it may hallucinate and give you, ChatGPT, right? Like it has a really good confidence when it tells you things, and it seems that it's telling you the correct things, but it actually can hallucinate and invent things if it doesn't have the information about it. So the problems with that one is LLMs can suffer hallucinations. We know that. Relevant information that beyond the scope of the training. So the information is actually frozen, and because of that, the LLM doesn't have access to the latest information. So anything that is not available in the LLM's memory or knowledge, and for example, things that are in the internet that is not in LLM's knowledge, then you wouldn't have access to that. And how do we fix this? I'm sure you know by now the term retrieval augmented generation, right? And everyone knows that now. And what that means is basically just giving the LLM what we call context, right? So we're giving the LLM the information that it doesn't know, and basically just send that to the LLM as context, and we leave the LLM to basically synthesize that and give us the answer based on the things that it knows and the data that we pass in as context. So that's why we need to do that, and to help us with the RAG system, we need the help of a vector database. It's a special database that contains that can persist what we call vectors, right? Has anyone been using or know what vectors are? I'm gonna be going through. There's a couple of things that I basically just want to impart in this session. This is very simple, I think, but there's a few things that need a little bit more explanation. So, in simple terms, right, a vector is basically a number, a magnitude with direction, right? So, a number and direction means positive or negative, right? And what does that mean? Like, in if you have a word, you can when it's stored in the vector database, it's actually converted into a vector, right? And a vector is really just a string of numbers. So, for example, it's an array of numbers, as I said here. And in Python, because we're dealing with Python here, we know that in Python an array is a list, right? So it's basically a list of numbers. So for example, the first example, we have a 3-dimensional vector, right? In this case, we've got 3 numbers in an array, basically, right? The next one is a 6-dimensional vector, and that means we have 6 numbers, right, in an array. And that's all that's all there is really in vector databases. But what does that mean, right? We hear when we hear vectors, we hear people say words like mathematical representation, or the words dimensions, or the term semantic search, right? So when you say a mathematical representation, it basically means for every word, or for every I guess data that you have, you can actually convert that into a string of numbers, right? So you can convert any string, any word, or any paragraph, or any any chapter. You can convert that into a x-dimensional vector, right? So basically, a sentence, you can convert that into a vector, right? Now, you also hear words like dimension. So dimension is basically the number of items in the array. It's quite subtle here, but what that really means is, I guess, step back a little bit. When you hear dimension, there are a lot of synonyms that you need to understand, right? So dimension, some people call it latent factors, right? Or some even call it features, or some even call it properties, right? So for example, I have an apple, right? That's an object. And for example, my embedding model has 3 dimensions. So 1, 2, 3, right? Just imagine that this vector represents an apple, right? The dimensions are called, remember, features or properties. So for example, this might be the size of the object, right? The first dimension. The second dimension might be the color, right? It's red, or it can be green. The third dimension might be, the hardness of it, right? Or something like that. That's important to understand, because in reality, the vector doesn't name the properties, right? So it just puts it in an array like this, right? So you have 3 arrays, you've got 3 properties, right? And same with this. If you've got an embedding model having 6 dimensions, you basically have 6 properties in that list, right? And it doesn't name it; it just properties there. And what does that mean, right? Like, I mean, sometimes okay, we hear the term semantic search. Semantic means the meaning of the words, right? So when we're searching a vector database, right, we don't typically we don't look for keywords, right? We look for the meaning. So when you look for if you have a question, when you go to the vector database, we look for the similar answers for that question, right? And then we return it to as a context to the LLM. So based on this, We can, when we store the data in the vector DB, we convert it into a vector, right? And then based on that, we can do similarity search that we can use for RAG. I have a further example here. Don't worry about the numbers. It's just, I just invented the numbers, but I hope, this will make sense what vectors are. For example, I have 1, 2, 3, 4, 5, 6 words: wolf, dog, cat, banana, apple, and walk. Imagine I have a 3-dimension vector, right? So as I mentioned, we've got 3 dimensions. That means we have 3 features. For example, the first feature can be pet. The second feature can be color. The third feature can be size, right? So for a wolf, typically vectors are, a number from 0 to 1, but it can be anything. It's just the magnitude. For example, a wolf, if it's a pet, then it's, close to 1. Actually, it's not. But the color, it can be 0.38. For size, it can be that, right? It's bigger than a dog, for example. So yeah, it's kind of like that. Each word has a representation of the vectors, right? And it can be, I guess, further explained in a chart like this. So here we've got 3 dimensions: feature 1, feature 2, feature 3. And imagine in the vector space, right, how it's represented in there. We've got 3 axes, so this can be feature 1, this can be feature 2, this can be feature 3. And, based on that, we can kind of, position those words. The words are already in vector representation. We can arrange that in the vector space. And what we find there is things that are semantically similar, or things that have the same similar meaning, are basically arranged close together in vector space. So you'll see that because dog and cat are pets, they're kind of close together. Wolf and dog are kind of canines, right? So they are actually close together. So, and it's a little bit far apart from, say, for example, something like a banana. But a banana is closer to an apple, right? So what happens is when we're actually doing a semantic search, for example, our query is a kitten, right? So the thing is, when we have a query, we actually convert that query into a vector, right? And then once you've got that vector, it's so easy for the vector DB to find similarities to it because it knows the things around it, right? So when you query is a kitten, it knows that a cat is close to it, a dog is close to it, but a wolf is also close to it. But the closest one is actually cat. So the most similar, I guess, object or word in there is a cat. I'm gonna stop and open for questions.
That's quite interesting, Jo, and it's quite good. I was wondering now whether the quantization, that compression, maybe this. Do you think this is sort of like related on how they are compressing the data? Because somehow you're pretty much converting everything to numeric values, which is quite impressive. As long as you, I guess, associate the numerical values in that particular.
Good question. And then I'm not quite sure if I know the answer, but I know for sure that the quantization doesn't affect the embedding, right? So if I'm working on, if I'm connecting to a cloud LLM, right? Versus connecting to my local LM Studio, regardless of what embedding model I use, it's going to be the same because I'm storing that embedding in the vector database. So it doesn't have any connection to the quantized state of your LLM.
I see.
Yeah.
It looks like Tony has a question.
Yes, please, Tony. Yeah, go for it.
Joe. That's a very good explanation. My question is actually, how do we choose how do we know the dimension of the vector? and how do we choose the properties or accordingly?
Yeah, yeah, again, good question. The answer is you cannot choose the properties, right? So I mentioned about latent factors. Latent means hidden, right? So the embedding model, depending on the embedding model, some have 348, 768, 124, 1024, 4096 dimensions, right? So my example, it's just 3 dimensions because that's the most that I can explain and visualize, right? Imagine 1,000 dimensions. That's so hard, right? But that's why embedding models actually don't name the properties. So I just put it here just so that we will understand it. In reality, we get this. Imagine 1,024, properties that basically describe that object, right? So it's really up to the embedding on how it generates it. And another question is how do we know the size of the embedding? Good question. Each embedding model, they can have different sizes, right? And it's easy to know the size. So what you do is you basically we'll go through that in our exercise. What we need to do is hit our hit our embedding model, send a text to it, whatever, 1 sentence, and get back the embedding. Based on an embedding, it's basically just a list of numbers, right? Once you get a list of numbers in Python, len array, right? All you have to do is do that, and then you've got the size of your embedding.
So sorry, just follow this answer. You mean we give like a document and they generate these vectors for us with a certain dimensions? Would this dimension would be a fixed dimension for the future? Like for instance, next time I put another document into that,
yeah,
maybe it's a much larger one.
Yeah.
Does it need a larger dimension, or still use the same dimension?
No, the same. Regardless if you pass 1 word or 1 chapter, if your embedding model is like 1,024, it's always going to be 1,024, right?
Okay.
Because when you're doing a similarity search, right, the vectors that you store in your database should be the same vector that you, the vectors that you use, the embedding model that you use to create the vectors in the database should be the same embedding model you use to embed, to create an embedding of your question.
Okay.
Right? Because otherwise it cannot understand, a different embedding model. Yeah.
So that means that dimension is sort of a configuration we defined at the very beginning.
Exactly. Yep. You hit the nail on the head. Yep. Oh my gosh. We only have 5 minutes and I have so many things to. Maybe we can continue in the next one, right? Like we don't have to have like module 4 next one, because I think this is quite important, and I only have 5 minutes left.
This is actually quite good. Yeah, we can do that, Gio.
That's good. That's good. Yeah. Okay, I hope that makes sense. And just imagine, right? The example is 3 dimensions, but the reality is typically you work with 768, 1024. You can never visualize that, right? Okay, so what vector database do we use? I recommend PG Vector. So SQL package called Postgres. Everyone knows SQL here, I hope. There's a lot of options in vector databases. The Melvus is kind of like the OG of vector databases. It's been here for a while. We've got Pinecone and we've got Chroma, all these things, right? But I still prefer PG Vector because, like, for someone like me who deploys regularly to the cloud, something like Postgres is very easy to I guess, convince customers to use, right? So everyone knows SQL, everyone knows Postgres. It's very popular in the development community, and it's battle tested, right? And then the libraries, say for example, many companies projects have using Postgres in one of their maybe transactions, right? So it's easier to convince a company to use PG vector in Postgres than trying to convince them to use something like a Pinecone or a ChromaDB, right? So because it's just people trust Postgres. At the start, Postgres had a kind of not so good reputation as being because it's a proper database and it has an extension functionality that can do vector DBs too. Many of these, I guess, standalone vector DBs supporters of them saying, PG vector is not good, but it's actually very, very good. I have here, if you click on this a benchmark, it's basically showing how PG vector is better than something like Pinecone, right? So I'll maybe have a look at it quickly just to understand. So here, I won't go into the details, but it's saying it's comparing Pinecone regards to queries per second against PG vector, right? So this is kind of using the latest index in Postgres, HNSW. I can't pronounce it. Hierarchical Navigable Small World, but anyway, that's one index that it's using. It's really fast, and Pinecone is supposed to be really fast, right? Because it's a standalone vector DB, but it's still fast, but PG vector is faster, right? So you can't say that PG vector is the wrong choice. Similarly here, PG vector is higher in queries per second. So anyway, that's just telling you that I'm not inventing this. It's a known a fact that Postgres can be a good vector DB option. Okay, I think I covered that. Any questions so far? We actually have only 2 minutes, so maybe later what you can do is try setting up PG vector on the Docker container. I have here the actual code you need to run to run PG vector in a Docker container, and what it will look like once it's up. If you have, I'm not sure if you want to use, I use dbeaver to basically talk to my database. So I have a dbeaver. It's kind of like an application you can use to talk to your database. You can see your database, what's inside the rows and the columns, and it will definitely aid us. As we're ingesting the data, we can actually see the data and how it's stored in the database. That's also one thing why I suggested us or to use Postgres, because in things like Pinecone and maybe Chroma, it's not that obvious, right? Like here you can actually see the database and how it looks like and work with it. So I thought it's probably a good option for us. Maybe next week we'll continue with this, and if you want, if you're up to it, you can do that assignments and look at. We've got one notebook in there to maybe give you a kickstart, and then hopefully if you run that, right, so we'll have more things to talk about in the next session. So I guess next session will be about vector DB still.
Sounds good. Yeah. Thanks, Jo. Thanks, guys. Yeah.
Thanks, everyone.
Cheers.
See you later. So quick, 30 minutes, right? That's fine. Yeah, that's cool. See you later. Bye-bye.